Welcome back. We want to continue taking a look at factor groups. So now at this point, we have essentially one thing in hand for this section, and that is that left coset multiplication is well defined when we have that the subgroup H is actually a normal subgroup of the group G. So taking that, we want to move forward and say, hey, we actually get this nice group that we will call the factor group. So let's take a look at our notes and see if we can show that indeed we do get this nice group. So our corollary to the previous theorem, now that we have that well-defined coset multiplication, this corollary states that coset multiplication actually defines a binary operation for the group G, what we might call mod H, okay? So G quotient H, G mod H, that sort of thing. G mod H is fine. Anyway, the cosets of H form a group G mod H under the binary operation given here. And what I'd like to do is I'd like to prove this, which is just a matter of verifying the three conditions that are required to have a group. Okay, what are those conditions? Well, we just have to have associativity of the binary operation. We have to have that the group contains an identity, and we have to show that the group contains inverses. So we just have to verify those three things. So first, our assumption, right, the given condition is we want to assume that H is a normal subgroup of G. And now that gives us that the binary operation is well defined, and it seems that we will make use of that throughout. All right, so for the first condition, we want to show associativity. Associativity. All right, for associativity, we need three elements. Let A, B, and C be elements of the group G, because that's how we identify our cosets. Then associativity says that if I take the product of two things, AH and BH, and then I take the product with CH, eventually I want to show that's the same as AH first, and then inside of the brackets, BH times the CH. So if I implement the definition here, the first step in our definition is to observe that this is going to be a H times, I'm sorry, a B times H times CH. And that, of course, is going to give us a B, a B times C, there we go, times H. So now we have the one singular coset that we're talking about, AB times C times H. But we have associativity in the group G, so we can actually rearrange this no problem right here as A times the quantity B times C. And now we can start to decompose this according to our definition of coset multiplication. So this is going to give us a H times BC times H. And then again, apply the definition of coset multiplication to get that this is AH times the quantity BH times CH. And this verifies for us the associativity of the binary operation. Thus, coset multiplication is associative. Excellent. We also want to verify the identity. So identity here. We want to let E be the identity in G. So G is a group, therefore it has an identity E. And what we can do is, well, one thing we can do is we can notice that E must be in H because H is a subgroup. And because E must be an H, if we wanted to talk about EH, that's the same thing as talking about just H. Because if this thing is in that set, then we may omit it. EH is just the subgroup H. This left coset is exactly the group. So we can express that. That's absolutely fine. What we want to do at this point is recognize that this is the identity element. But I'm going to do that by noticing that H times AH is equal to EH times AH. No real issue there. But this is E times AH. But of course, that's just AH. So I have taken this thing and gotten AH back, and that's no problem at all. But what I'd like to do is I'd like to recognize that I can multiply on either side. So I'm going to write this as A times EH. Let's see, that's in parentheses, which is the same as AH EH. I'm not sure that it's necessary for us to show that it's both ways, right? We know that we're working in, well, I suppose we're trying to show that we're working in a group. So still left and right matters. A, E, and, oh, yep, of course, that's A, H, just times H. So I can multiply on the left or I can multiply on the right. Both of them are equal to AH, and that's what I wanted to show. Thus, H or EH is the identity in G mod H. All right, so we have associativity, we have identity. Now I just need to verify inverses. So let's see here. Let A be an element of G, and I want to verify that we have an inverse within our coset. So let A be in G, then what I'm interested in identifying is the inverse of AH. So this is in G mod H. Okay. Since A is an element of G, A inverse is also an element of G. And we get that. To write this kind of nicely, we can have it as A times H times A inverse H is equal to A times A inverse H, which is just H, the identity element. And again, I'd like to verify that the order of multiplication doesn't really matter. So I'm going to observe this as A inverse times A inverse times A times H, which of course is the same as A inverse H times A H. So each element has an inverse. Thus, for each A H in G mod H, its inverse, let's see here, I suppose to write it more appropriately, its inverse, which should be written in this way, is A inverse H. That is, it contains inverses. Thus, G mod H is a group. And that is precisely what we were looking to show. So we just implemented the definition of a group for this particular example, right? G mod H. It's kind of a particular example. We didn't really specify what G is or what H is, but we know the properties that are necessary in order to show that this is indeed a group. And then the last thing that we want to mention is that, hey, yes, this word that we were looking for, factor group, or this pair of words, factor group, or quotient group, is what we call this thing G mod H. So the factor group, G mod H. And that is just fine. Excellent. So join me again. We're going to take a look at another theorem, yes, and then we're going to take a look at a bunch of examples. So join me back here in the office for another theorem, and then we'll take a look at some examples.